electrophilic substitution, and this is a reaction that benzene can undergo. So I'm going to just do a little bit of reminding you about benzene that you did in the bonding topic. So benzene, you learned you can draw in two ways. I haven't taught benzene other than you spec, right? So there's some slight differences. So if you don't know all of everything I'm saying, don't panic. You've been taught what you need to know for it. But benzene is C6H6, right? Each of those vertices has a carbon, or is a carbon, and has a hydrogen on it, so C6H6. And you can draw benzene either in the Kekulé structure or the kind of delocalized version. And we say that the Kekulé structure is a representation of kind of one extreme of the two possible resonance forms. So with those pi electrons dancing around, there's 6 pi electrons, 2 in each of the double bonds, that are dancing around there. So the delocalized structure is the more accurate one, and we know that from some evidence. We know, and I can't remember whether you need to know this for the new spec, but we know when we look at benzene under certain circumstances, we can see that the bond lengths are all the same. Did you cover that? But in the Kekulé version, they should be different lengths. So you'd expect, if Kekulé was right, that the double bonds were shorter and the single bonds were longer, and it would look, in an extreme example, like that, to take it to its extreme. But it doesn't. All the carbon bond lengths are the same as each other, so it's kind of like having 1.5 bond strength. And we can also see it from the some other processes. And again, I can't remember whether you've covered this or not, but what we can do is look at the enthalpy of hydrogenation. So we react benzene with H2, we get cyclohexane, and that is an exothermic reaction. So you taught about benzene being stable, but cyclohexane is actually more stable, which is slightly surprising and confusing for people. And that's an exothermic reaction, so it looks something like that, right? Energy there, like so. But if Kekulé was right, then these would be 3 double bonds, and the energy energy released when you hydrogenate an alkene to form an alkane is 120 kilojoules per mole. So you'd expect, if you're hydrogenating 3, you'd expect it to be minus 360 kilojoules per mole enthalpy change, right? Does that sound familiar? But in fact, it's less exothermic than you'd expect. It's not 360. It's more like, I can't remember the number, it's like 208 or something. It's a smaller number than 360. And that tells you that benzene is more stable than the Kekulé structure would have told you. So it's only like 2, I can't remember the number. Can anyone remember it? Is it 208? Look it up if you don't take my word for it, but it's a smaller, it's less exothermic than you'd expect. Okay. Other things that you learn about benzene is that it's less. Does that sound familiar? Or does that make sense? What I've just said there. I'm happy to take my time. If you want me to go over that, I will do. Talk to me. Yeah. Yeah. I'm just going to go through this again a little bit more stepwise. So, are you happy? First of all, the alkene to alkane, that process, the enthalpy change there is equal to minus 120 kilojoules per mole. You can measure that using enthalpy change calculations, right? And so if Kekulé was right and this was the structure, you'd have to hydrogenate 3 double bonds. And so you'd expect that to be 3 times that number. So you'd expect it to be minus 360 kilojoules per mole. Okay, but it's not. It turns out that benzene, the difference between benzene and cyclohexane is smaller than you'd expect, and you only release a bit less energy. And if no one's given me an answer they can remember, but let's say it's minus 208, let's pretend I'm right there, kilojoules per mole. There's less energy released than you'd expect. It tells you this reaction is less exothermic, and so there must be a smaller gap between them, and therefore this is more stable. So benzene more stable than predicted from Kekulé's structure, so more stable. So that's the second piece of evidence that benzene has got this resonance delocalized structure. A third piece of evidence is that benzene doesn't undergo the same reactions as alkenes. So alkenes, you know, don't you? Because we've done this quite recently. Alkenes can undergo electrophilic addition reactions to form halogenoalkanes. And we've learnt the mechanism for that as well if I draw the mechanism out, just to remind you, we learnt that the double bond attacks the hydrogen there. The hydrogen is acting, or the HCl is acting as an electrophile, an acceptor. So you write the definition of electrophile if you need it, as an acceptor of a pair of electrons. It's forming a bond there. That causes that bond to break. We get the carbocation intermediate. If you've forgotten this, we've done it loads, so you need to practice it, right? I'm not going to go through this one in too much depth. And then that attacks there. We end up going up to... Sorry, there's a chlorine here, isn't there? Addition. So the electrophilic addition reaction takes place with alkenes, which you don't need to write that out because you've done that 100 times and you've learnt it by now, hopefully. But benzene, it's meant to be a benzene, doesn't react in the same way because benzene is quite stable. So 2 bits of evidence that benzene is resonance stabilized, okay? Another piece of evidence is that if you have a, let's imagine you can do a reaction, I'll show you how they work in a minute, but if you can dye substitute a benzene ring, if it's a resonance formed or the kind of delocalized version of it, if it's dye substituted, and I'm going to call the substituents X, right? That's one possibility. That's another possibility. And that's another possibility. It's 3 possibilities. Either adjacent, which we call ortho, which you don't need to know the ortho, by the way. 2 places away that we call meta. Again, you don't need to know the meta term. Or para, when they're opposite each other. Okay, you don't need to know the notations. But if Kekule was right, there'd be a whole load of possibilities of this. There's only three dye substituted isomers. So we've got that's one, or we've got that one where X is at either side of the double bond or either side of the single bond. So you can see how you get more possible isomers, or more possible dye substituted isomers, and it turns out there are only 3. So this must be right. Again, it's another piece of evidence backing up that that benzene is delocalized and that all of the carbon-carbon bonds are equivalent. So it's all showing that equivalency. So greater stability, less reactivity, bond lengths all the same, the number of dye substituted isomers, right? This is all stuff that point to benzene being as it is. Now what you need to know is that benzene can undergo reactions under quite harsh conditions. Now they've really stripped away in the new syllabus how much of this you need to know. I did make some notes I've not got, but never mind. So you need to know that benzene can react with an electrophile, and it does say you don't need to know how the electrophile forms now, but I'm going to give you one example of it so you can see, and you'll see it in the textbooks and revision guide, but it does say you don't need to know how the electrophile forms. And remember that each of those carbons has got a hydrogen on, so that electrophile represented by E, as per the specification and the textbooks, that E will replace one of the hydrogens, and that will leave you with H+. So that's the overall process of electrophilic substitution. So E representing an electrophile, which is a lover of, I beg your pardon, so lover of negative charges, but so we should really say acceptor of pair of electrons. So a bond can be made between carbon and the electrophile through through a reaction. Okay. And so the hydrogen that was here, and you could imagine there was a hydrogen there that ends up as H+. So that's the overall reaction. And you need to know the mechanism of electrophilic substitution as well. So I'm going to draw the general mechanism to start with, then I'll give you an example. And I don't know what they're going to do in the exam. To me, it makes sense that they're going to give you examples that you've not seen before. So I might as well show you one or two of them and try and get you to learn them. It won't do you any harm. But we'll do the general one to start with. So the way that it works is that this circle here is representing those 6 pi electrons. We're going to form a bond between one of the carbons and the electrophile. So how many of those electrons end up in that single bond there? That's a stupid thing to say. Just ignore me for a second, right? I don't really like the way I'm going with this. Anyway, let's start again. So I'll just tell you. So that those 6 pi electrons there, what I'm trying to get at is 2 of those electrons, or 2 of those 6 electrons end up or attack that electrophile. This is an extremely reactive electrophile, and we'll see an example of that in a second. So that can happen, and what that results in is the formation of an intermediate. Now, how you draw this intermediate has to be just so. What I'm drawing is fine, but I think it's not helpful how I want to explain it. So I'm going to get you to draw a line through that, and we're going to change it a bit, okay? So it's wrong. It's not wrong, but I'm trying to make it as easy and make sense to you as much as possible. So I know some of you don't like messing up your notes. I apologise, but I'd rather get it to make sense. So I'm not going to draw the hydrogen on there. I'm going to show this arrow coming through one of the carbons. You don't have to show it coming through one of the carbons, but I quite like to because it shows you that you're forming a bond between that carbon and the electrophile. So that's why I did that. And drawing the hydrogen on the carbon below probably added to confusion, right? So just get rid of it. Now, so what you're going to end up with is a bond now between that carbon and the electrophile. But the bond with the hydrogen that was there is still there. That's still there. So get to that point, and I want to explain something, then we'll go, we'll carry on drawing. So drop your pens when you got to that point, so I know you're all with me. This is the last mechanism, by the way, so we'll just practice and practice these until you can all do them. Now, remember, this circle is representing 6 electrons. 2 of them have now become this bond here. So how many are left? Well, 6 take away 2 is 4. And so it's not a full circle now, it's a kind of 2/3 of a circle. And the way that you draw that semicircle is with the opening to that semicircle pointing to the carbon that has the 2 substituents, the electrophile and the hydrogen on. Right. And then you have to show, though, that the ring now is positively charged. And we put a plus right in the middle of the ring. Inside what would be the circle, but that semicircle is, please highlight to yourself that that opening to the circle is pointing to that carbon, and that's the intermediate that's formed. That thing is really quite unstable. Now, just going to go back to... No, I'll come back to that in a second. The thing that happens next is that rather than... Let's go back to this a sec. Rather than it being an addition reaction, like you had before, where the negative charge thing that spat out combines with that carbocation to form an adduct, an addition product, instead of something coming to that to make an adduct here, that would break aromaticity. So this is really unhappy, but we know that being 6 pi electrons, we know that aromatic systems are really stable. So and this is another piece of evidence of the aromatic nature of benzene, is that it undergoes substitutions. And so what it does, aromaticity is reformed because of those 2 electrons in that bond become pi electrons to reform that aromatic system. So we draw an arrow from the center of that bond. Now people always draw this arrow in the wrong place, so be really careful. It starts from the center of the carbon-hydrogen bond, and then you just point it towards the plus charge, and we end up then drawing the product we know forms, which is the electrophile is now up there, and the hydrogen is plus. So that's the mechanism we need to learn.
What's aromaticity?
Aromaticity, forming an aromatic ring, a benzene ring.
Oh,
Yeah, so that resonance stabilized aromatic ring, benzene ring. So benzene is C6H6. Aromatic rings are anything that have got this delocalized 6 pi electron system, or 6 pi, 10 pi, 14 pi, 18 pi, but stuff you don't need to know. And it can be in molecules without, they'll all have to be carbons. You don't learn, but yeah, the aromatic is a general term for this resonance stability you get in benzene. Yeah.
In the example, let's talk about the aromatic.
No, just talk about the resin. You would just draw the pictures.
Okay.
I'm trying to commentate on the pictures as detailed as I can, and accurately as I can. So resonance stability would be the language that you would use. The benzene ring, I guess. But aromaticity is fine as well. Okay, so that's it, right? That's the mechanism. So it's not overly long or complex, but let's do an example then. And you'll see when you look at the textbooks, which I'm trusting you'll all do, that there are maybe a couple of examples, and it does go into these in detail. But it does say in the spec you don't need to know how the electrophile forms. That doesn't mean you don't need to know examples of it. So here's an example of this. So if you take benzene and react it with nitric acid, in the presence of its concentrated nitric acid, by the way, and you use concentrated sulfuric acid as a catalyst, the little C there is showing that it's concentrated. So C equals conc. And conc nitric, a lovely combination of 2 lethal chemicals in a pot together. Lovely jubbly. What you end up doing is forming a nice explosive nitrobenzene. And by the way, if you do this multiple times, you get trinitrobenzene, or a related compound trinitromethylbenzene, otherwise known as trinitrotoluene, otherwise known as TNT. You'll know why we tend not to do this in the lab too often if we can avoid it. So this is the way that TNT is made, by the way. It was made by, I think it was Nobel invented TNT, dynamite. I'm not sure the dynamite is TNT, it's the same stuff. No, which was nitroglycerin? Anyway, it doesn't matter. Alright, anyway. Plus, now be a little bit careful here. So this is an example, but you might get a different or similar example to this. It can't be H plus the product. Look, NO2 has gone, the H from here, and one of these oxygens are left over. So what are you going to get? Well, obviously water. And the sulfuric acid is catalytic. So the mechanism of that is as follows. So step 1 is the formation of the electrophile, not in the spec, but I'm going to show you how it forms. So nitric, again, because they might show you something like this and show you the electrophiles, I want you to be familiar with it. So if you take And there is something, I'll tell you what's in the spec on this. So if you take nitric and sulfuric acid that are concentrated and stick them in a pot together, warm them up a little bit, what happens is you form the electrophile NO2+. You also form HSO4-, and you form H2O. There's the H2O that ends up over there. That's where it's gone. Okay, so it formed in that first step. But this is the electrophile, and notice that the electrophiles for this are always positively charged. So this is the electrophile. Very, very reactive, will react with the benzene ring. They're quite unreactive benzene ring. It's extremely reactive. Now, the one thing that is in the spec, or I have seen questions in this course, is what kind of reaction is going on here? How would you class that reaction? I'm going to pause the video, give you a chance to discuss. So in this reaction, the H2SO4 is acting as an acid, and what's happening there is that the nitric acid is being don't write this down. You write this down. The nitric acid is being protonated, and the sulfuric acid is being deprotonated. So this funky thing forms, which then collapses down into NO2+ and H2O. You know, who knows? You could be asked to draw NO2+ as a dot cross diagram. Imagine, can you do it? It's a little challenge for you. Not now, but think about, can you do that? But anyway, so NO2+ is an electrophile, and it then reacts exactly as I've just taught you. So the NO2 is the electrophile. That arrow starts from the circle, attacks the NO2, giving that semicircle thing with the plus and the H in the NO2, and then the aromatic ring, the aromaticity reforms. Being really careful where we start and finish our arrows. I'm sorry that's so small. It's not too bad on your screen. Notice where I start it and finish it, and then that ends up giving the nitrobenzene and H+. Now this last step is in all the textbooks, but I don't really like it, and I'll tell you why. But it's saying that this extremely strong acid reforms, okay? But it's just showing you, I mean, the point of it is to show you that sulfuric acid is acting as a catalyst. And you know, don't you, the definition of catalyst is something that is unchanged through the course of the reaction. But it doesn't make a lot of sense to me that H2SO4 will actually reform. It will probably stay as this because it's a very strong acid. But anyway, that's the mechanism there. So that, folks, is electrophilic substitution. You need to now practice and learn that mechanism. And when you do past papers, you will see bits of organic are different, and what they expect you to know for electrophilic substitution is slightly different. But I've taught you enough that you can see it. I think I might show you another example of this. Why not? So another example of this. Again, a reaction that isn't in the spec. You don't need to know it, but it's an example of a reaction which can take place. So if you take something like chloromethane in the presence of aluminium trichloride, we can form that plus HCl. Okay, now that's not obvious, but we know the mechanism. We know there's only one reaction of benzene we need to know, and that's this electrophilic substitution that we're going to learn and practice. And so, I mean, in this particular case, I've given you the product, so it must be that CH3 plus must be our electrophile. And again, you're not required to be able to do this step, but it might ask you something along the lines of what's going on here. and you should perhaps be able to work out that an electrophile CH3 plus is formed, and you know it comes from that reaction there. So there is formation of electrophile, but the thing you would be expected to do is to take that electrophile that's formed in the first step and react it with benzene and show that mechanism. So this is exactly the same, and you'll see there's loads of examples of this if you start sniffing around textbooks. They're the same every time. It's always the same. Always a plus in the middle of the semicircle. Always one of the carbons with 4 things hanging off it. One of them being hydrogen, the other one being what was the electrophile, and then that H plus falling off to reform the aromatic system, the benzene ring if you like, to give H plus. And just for completeness, just to show that the AlCl4 in this case reacts with the H plus to reform the catalytic AlCl3 and forming the HCl as the product. So you can kind of work through and see maybe what's happening in each case. But the key thing is this step you need to be able to do. Even if it's an unfamiliar, there's loads of possibilities, unfamiliar electrophiles, and some of you will have the sense to kind of have a nose at other examples of electrophiles there. So I'm going to stop there.